Hello guys, welcome to this yet another YouTube video in which I'll be discussing complexity. This video is based on a recent video released by Sabine Hosenfelder. I'll drop a link, of course, obviously in the description, and I'll give it in the end screen as well. But in this video, I'll be discussing complexity in my own way, of course, but by taking inputs from that video. Yeah, let's get started. Now, when you think about the future of physics, most of you probably think of the theory of everything, or the unified field theory, the holy grail of physics, and uh, the like. Now, however, the next big thing in physics might not be the discovery of the unified field theory, but a better understanding of complexity. If you think about it, progress in theoretical physics has stalled in the last few decades. The last significant achievement was the discovery and partial verification of the standard model of elementary particles. But since then, theoretical physicists have been engaged in a seemingly futile battle to unify general relativity with the other three forces of nature. Gravity with the other three forces of nature described by quantum field theory. And there have been numerous theories like string theory, loop quantum gravity. However, so far, none of these theories have been able to satisfactorily answer all questions or garner enough experimental support to be taken seriously as a scientific theory. So this has led some physicists to wonder whether it's even possible to unify gravity with quantum mechanics. And there have been a lot of new approaches like semi-classical gravity and so on, but we'll keep that for another day. Now, although progress in theoretical physics has been discouraging, scientists have been making huge progress in the fields of complexity research, chaos theory, consciousness research, emergence, artificial intelligence, etc. Of course, artificial intelligence is probably the talk of the world right now. So the first question I would ask is, are we still talking about physics? Answer is an emphatic yes, because see, for instance, if you were to suggest about 3 decades ago that physics and consciousness are somehow related, most people would disagree with you. They would say consciousness is not science, it's philosophy or metaphysics. And even if consciousness was to be explained by science one day, you'd be told it would probably be done by neuroscience, the science of the brain, since that's where consciousness most likely emerges. But today, according to many prominent scientists and researchers, consciousness can be explained by studying complexity and emergence, and all that's physics. So what is complexity? Of course, it's a measure of how complex something or some phenomena is, or how non-simple it is, or how difficult it is to understand, describe, and reproduce. But we're looking for a quantitative definition of complexity, obviously, not a qualitative one. To be of any use in the physical sciences, we need a quantitative definition. Now, this is where things get difficult. There are many ways to define complexity, and since complexity is a relatively new and less understood topic, there's no general consensus about the best way to define complexity quantitatively. What makes things even more difficult is the fact that complexity is of significance in many disciplines like physics, mathematics, computer science, and biology. So physicists are interested in the particular aspect of complexity and are seeking to define it accordingly, but computer scientists are probably looking for a different definition. So physicists want to define complexity quantitatively in such a way that they can use it to formulate new laws of nature. One way to think of complexity is to think about the system's predictability, like how difficult or how easy it is to predict the behavior of the system. The more unpredictable a system is, the more its complexity, obviously. A human is more complex than a rock, obviously, simply because it's much more difficult to predict a human's behavior or actions than a rock's. If you know how the material the rock is made of behaves, and if you know the condition of the surrounding environment the rock is kept in, then you can predict the behavior of the rock. Of course, it's not simple and surely not possible in practice, but it's much simpler than predicting the behavior of a human, obviously. Because to do the latter, you have to have a detailed knowledge of the precise neural circuitry in the brain of that human, a detailed knowledge of biology and human anatomy in general, a detailed knowledge of the surrounding conditions, and a lot of other things. Probably the most popular measure of complexity is algorithmic complexity, also called Kolmogorov complexity. It's simply the length of the simplest computer program that can completely describe the system we're trying to measure the complexity of. So basically, see, this is not of much use to physicists, since the algorithmic complexity of everything in the universe from an atom to a galaxy is exactly the same. But obviously, a galaxy is much more complex than an atom. But why is the complexity, at least the algorithmic complexity of an atom and a galaxy, of everything in the universe, pretty much is the same? Because everything from an atom to a galaxy is made of the same elementary particles, or the fermions, and they interact via the same elementary particles or the bosons, and Even if you leave gravity out of the bosons, like we don't yet have any evidence for graviton yet. So that even then gravitational interaction is described by the exact same mathematics of general relativity, regardless of the objects between which gravity is acting. Now, so basically the same theoretical framework or the same mathematics describes everything in this universe from an atom to a galaxy. And so basically they're all described by the exact same algorithm. So if you're trying to pin down the algorithm, then the algorithmic complexity of a rock and a human would be the same. But that's not of much use to us, obviously. So what is it that separates a human from a rock? Surely not the constituent particles, because every element is made of molecules, every molecule is made of atoms, and every atom is made of electrons, protons, and neutrons, or if we go further, electrons and quarks, basically the same elementary particles. The elementary particles that make up a rock are exactly the same elementary particles also make up a human. So it's not the constituent particles that define that can be used to separate a rock from a human. Like obviously a rock is different from a human, but they're deep down they're made of the same particles. So what is the key here? What is the difference? The key is the arrangement of the constituent atoms and also in the interaction between them. So the particles in the rock are arranged differently and in a much simpler fashion than in a human, obviously. And of course, the number of particles also play a role. Like the number of particles constituting a human is a lot more than the number of particles making up a rock. But the key is the arrangement of these particles. So it seems that we need some measure of structural complexity, some complexity that would take into account the structure of the system or the arrangement of the system, arrangement of the particles that make up the system. So it seems that some measure of structural complexity would be much more interesting to us than algorithmic complexity, and that is true. However, we are still missing something here. See, although we take into account the structure of the system when we talk about structural complexity, but we completely ignore the way the system was assembled. Like there are many ways to assemble a complex system. In the end, all of these assembly processes will result in the exact same system structurally. Like suppose we have a complex system, we can assemble it like this, then we can assemble it in a much more complex way. Like think of it like this. You want to reach from point A to point B, the simplest path would probably be the straight line path under the normal circumstances, obviously. But suppose you can you want to reach point B from point A, but it's also possible. It's a possible path. Like if, suppose you go from point A to some point C, and from C you go to B. That's also a possibility. Now, in both of this, this is just a rough example. Okay, so in both of these cases, your ultimate destination is point B. So your destination is the same, but the path followed is not the same. The time taken to travel from A to B is not the same in both the cases. So here it's something like it's somewhat similar. We have to take into account the way the system was assembled. Like there are many ways to assemble a complex system, and in the end, all of these assembly processes will result in the exact same system. Structure, the structure of the system will be the same, no matter how we assemble it. But some of these assembly processes will be simpler and quicker than others. So in some sense, the systems assembled according to these simpler and quicker assembly processes are less complex than the other systems, simply because it's easier to build them. We have to take into account how we build the system, because the system did not just come into being, right? We're just not measuring the structure complexity of a system which was already there. We have to take into account how we build the system. That's because that's what will be useful to us. So this problem is solved by a novel and promising theory called assembly theory. Assembly theory measures complexity based on how difficult it is to assemble the system. To assemble big and complex systems, we first need to build the shorter parts of the system. And since there are different ways to do this, like we could build this part before that or that part before this and so on. So assembly theory introduces an element of history dependence in complexity. There is also an element of selection, like in selection in what sense? You can think of it along similar lines as natural selection. Like some things assemble, but they fall apart and are gone due to some accidents or maybe due to some because they violate some scientific principle maybe. So some things assemble, but they fall apart and are gone because they're unstable. But whereas some other things that assemble, they remain, and since they remain, then they like they survive kind of, and then they multiply, and the copies that are produced, they also do the same. And occasionally they change themselves slightly in response to external conditions. So this is just like evolution and adaptation, just like natural selection and adaptation in biology. So in other words, this is a kind of evolution of a complex system. So that is the first key feature of a complex system, evolution. Keep in mind, evolution. So yeah, we talked about an element of history in assembly theory. Now, this element of history is extremely important. If you're looking to quantify the complexity of an object using assembly theory, for instance, in some cases, we might want to consider the complete history of the system. Complete history, what do you mean by complete history? Because see, for instance, consider synthetic elements or elements that do not occur naturally, but but have been synthesized in the laboratory by humans. Now, of course, a synthetic element is structurally less complex than a human. Of course, like human synthesize the element. And anyway, it's an element, so it's much less complex than us humans. Yeah, it's much simpler to assemble a synthetic element than to assemble a human. So from this, most of us would conclude that okay, a synthetic element is less complex than a human. However, humans assembled the synthetic elements. The synthetic elements did not come into being by themselves, but humans, we came into being by ourselves. Like, right. So humans assembled the synthetic elements, and humans probably weren't assembled by God. Humans were the result of a long chain of events starting off from a random accident. Like in other words, what I always say, ordered complexity is a fortunate product of random processes. Like that's the most likely view anyway. So anyway, the point is synthetic elements would not exist without humans because humans built synthetic elements. So in a certain sense, to build a synthetic element, you have to assemble a human first, right? So from this perspective, synthetic elements are more complex than humans. Sounds counterintuitive at first, but yeah, when we say synthetic elements are less complex than humans, we are already making the assumption that humans exist. So in some cases, by history, we refer to the entire or complete history of the object's assembly starting from scratch without assuming the existence of any other complex system like humans. I hope you get this. So the history of assembly of a complex system is important because only by studying this history can we explain all aspects of the system. Theoretically, there are a lot of possibilities, but due to some historical accidents, some of these possibilities don't occur and others do, like kind of selection, what we discussed, affecting greatly how the final assembled system turns out to be. For example, Newton's laws can explain the motion of the planets around the sun, but not why the planets of the solar system move in the same direction. Like, yeah, but it could be possible. Like if suppose the planets are moving in different directions, like this planet is moving in clockwise, but the other counterclockwise, that would also have been, possible. Like that would not have violated Newton's laws. But so yeah, Newton's laws explain the present solar system that every planet is moving in the same direction, but it doesn't explain why this has to be the case, like why this is the case. And it probably cannot be explained by any scientific principle. And this is where the concept of historical accident comes in. The thing is that this is because, the solar system condensed out of a rotating disk of gas. A disk of gas was rotating, and from there, all the planets were formed. And since the disk was rotating in one direction, obviously it's a single disk, so it will rotate in a single direction. So all the particles, all the planets, they were hurled in that same direction, and then they continued rotating in that same direction. But this was just an historical accident. It is entirely conceivable. It could have been possible that suppose one planet comes like this in a clockwise direction and the other comes like this, and then they rotate in different directions. That could also have been possible. So such accidents, these are just historical accidents, and such accidents are not inevitable, but neither can they be explained in any way. So this is why it's important. Like in short, we can like if you want to fully explain every aspect of the system. Suppose let's take solar system to be a complex system. If you want to explain this also, then we need to take into account the history. This is why the historical part is important. Yeah, so in short, we can conclude that to study the complexity of a system, we need to study the evolution of the system. The term evolution captures the assembly history of the system, the selections that shape the assembly process, like the natural selection, and the way the system responds to feedback and improves itself, adaptation. Now, all of this information cannot be gathered just from the structure of the system. We need to understand how the system came to be and how its structure changes over time. So the first important feature of a complex system is evolution. But there's one more, the next, and that is, of course, emergence. Another important concept related to complexity is emergence. Now, what is emergence? In a complex system, I have already discussed emergence in a couple of previous videos, but anyway, I'll discuss it here also, don't worry. So in a complex system, studying only the parts, a complex system means it's presumably it's made up of a lot of parts. So in a complex system, studying just the parts will tell you nothing about how the whole system affects an individual part and how they interact with one another. Like when many simple parts are interacting in a complex manner, then emergence simply refers to the emergence of new properties of the system as a whole, which cannot be explained by studying the individual parts or which do not arise from the properties of the individual parts. Like an example of emergence is wetness, like water or any liquid, it is wet. But the atoms, take water for example, the atoms or molecules that make up water are not individually weight. Like you didn't say an H2O molecule is weight, a single H2O molecule is weight, of course not, or a single hydrogen or oxygen atom is weight. But wetness emerges as a property of water as a whole. When a lot of hydrogen atoms, I mean H2O molecules are arranged in a particular pattern, then we get liquid water, which is wet as a whole. But if we arrange these same H2O molecules in a particular this sort of pattern, like then we get ice, which is not wet, like ice is solid. And if we arrange it in a different pattern, in a much more loose pattern, then we get steam or gas, which is just vapor, which is again not wet. But they're basically the same thing. They're just water molecules. They're just water. So this is so we can say wetness is an emergent property of water. We cannot explain or study wetness just by studying the molecules of which water is made. Now, according to reductionism, which is roughly the opposite of emergence, everything can be explained by breaking them into smaller and smaller pieces and studying these parts. But this might not be true because in complex systems, we cannot predict or explain all properties of the system just by studying the parts it's made of. For instance, water has some properties which neither hydrogen nor oxygen has. For instance, water, like we all know, water extinguishes fire. Like if you pour water on a fire, the fire will die down. But oxygen, on the other hand, oxygen is required for fire to burn. So oxygen doesn't have this property of extinguishing fire or suppressing fire, but water does, and water is made of oxygen. So if you just study the oxygen and you say that oxygen has this property, so water which is made of oxygen should also have this property, then you are absolutely wrong. So in this sense, we can say that this property of water by which it suppresses fire is an emergent property. Then wetness is also an emergent property. So I hope you get the idea. Now, so what is the key is that the arrangement of and the interaction between the parts also play an important role. Okay, like of course, like I said, the arrangement of H2 molecules can make water or ice or steam. In fact, this might be why consciousness cannot be understood just by studying a single neuron in the brain. We need to study the whole brain, which is an extremely complex system, not process, system. So the point of interest is that it's not possible to completely describe a complex system just by studying the parts it is made of. Now, whether this is due to our current shortcomings or limitations, or whether it's fundamentally impossible, that is obviously the next important question. And this question gives rise to two kinds of emergence. One is weak emergence and the other is strong emergence. Weak emergence is not really emergence at all in the true sense, because according to weak emergence, it's possible in principle or in theory to completely describe a complex system with the knowledge of its parts. Then you would say that then like the examples I gave you, like water and oxygen, the fire extinguishing property, then how can it be weak emergence? So yeah, like according to weak emergence, it's possible in principle to completely describe a complex system just with the knowledge of its parts. However, we haven't been able to achieve this feat in practice due to the fact that the system is much more complex and sophisticated for our current calculational and computational power to handle. Right. So you cannot be entirely sure that with a supercomputer of almost infinite computational power, we cannot simulate a complex system with just knowledge of its parts. Okay, however, like, yeah, maybe the arrangement matters, the interaction matters, but maybe we can all just, with just knowledge of its parts, we can reproduce the properties which seems emergent to us. However, it's not possible today. Like, yeah, it's not possible today because, and seemingly not anytime soon, but that's just because of our limitations, our current limitations. Simulating the behavior of trillions of particles is no easy feat, even for today's most powerful supercomputers. The point is, according to weak emergence, this is just a matter of our limitations. We do not need fundamentally new kinds of laws to explain complex systems. Or in other words, the same basic principles apply at all scales, from the most simple to the most complex. Now, for our ease of understanding, for our ease of developing our theories or hypotheses, we may formulate new laws of complexity that describe the complex systems. However, these are not fundamentally new kinds of laws. Emphasis on the word fundamentally. In other words, these laws are at least in principle reducible to those basic laws. On the other hand, strong emergence. Now, strong emergence claims that we need fundamentally new kinds of laws to study complex systems. Complex systems represent new and independent laws of physics. Independent in the sense, like, this cannot be, even in theory, even in principle, these laws cannot be reducible to those basic laws. They are like fundamentally new kind of laws, entirely new laws. In a universe governed by strong emergence, it's impossible, even in principle, to fully describe a complex system just by studying its parts. It must be noted that weak and strong emergence, like they're not kind of, they do not disprove each other. And so like it's not like if strong emergence is true, weak emergence cannot be true, or the other way around. Like some complex systems may be weakly emergent while others may be strongly emergent. That's completely possible. So what is certain is that further research on emergence is crucial to better understand complexity. And of course, more the number of emergent properties in a system, the more the complexity of the system. More the number of emergent properties, the more the complexity, obviously. Because more emergent property means more unpredictability and the more complexity. Complex because it's difficult to predict, and that means it's difficult to describe. We need much more information to describe it, and that means it's in that sense it's much more complex. So we described two important features of complexity, and that's emergence and the previously evolution. And yeah, like we can roughly see that there's a link between the two. Like as a system evolves, a lot of new property emerges. So more a system evolves, it's likely to be more complex. And similarly, more the number of emergent properties in a system, that it will be more complex. And more a system evolves, the number of emergent properties will also be more. So it all kind of fits in. Now the last point. See, whenever we're thinking, like we start thinking seriously about the fundamental nature of reality, the first question most of us ask ourselves is this: like, why is there something rather than nothing? That's a metaphysical question again, but yeah, that's a very logical question to ask. Because see, that would have been most simple, like nothing exists, nothing, no matter, no consciousness, no laws, or nothing. That's the most orderly state. Because like you'd need, like that's most orderly state, and you can say most simple state, because nothing is there. You don't need any laws or anything to describe, because there is nothing to describe in the first place. That's the most simplest state. But however, it's clearly not possible that nothing exists, because something must exist. Like we are here asking these questions. Now, what is this something? Is our universe the most complex and unpredictable system possible? Like that's basically chaotic system? No, clearly not. See, the most complex and unpredictable system it means complete chaos. That's the most complicated system. Like nothingness is the most simple system, and this is the most complex system. Because see, the most complex and unpredictable system, like I said, that means complete chaos, and chaos implies unpredictability. Because as we know, like a small change in the initial conditions of a chaotic system will have drastic consequences on the future behavior of the system, thus making it or rendering it unpredictable. This is technically called sensitivity toward initial conditions, or to use the more popular term, butterfly effect. So as the complexity of a system increases more and more, it moves closer and closer to chaos. And when it is closest to chaos, this is what we refer to as the edge of chaos. But so when it is closest to chaos, but has not become fully chaotic, it's just at the edge of chaos. It has not become chaotic, but it's closest to chaos. That is the crucial state. This is where the magic happens. So at the edge of chaos, at this stage, it is the most complex. At this stage, the system is not totally unpredictable, because if it was totally unpredictable, it would have been chaos. But there exists a lot of variety in the system, and making it more complex and much more difficult to predict. But it's not fully unpredictable as well. So now the world around is clearly not fully chaotic, because there are certain laws, there is some order. Of course, there is some amount of randomness in this order as well, because it's not full order. It's not like nothing exists. And life exists. Life needs some order, some stability, some properties that remain constant over an appreciable period of time. Like not over a long period of times, obviously, but over some period of time. So life simply can't exist in the most unpredictable universe. So we are neither in the most simple, most orderly system, that's nothingness, and nor we are in the most disorderly system, that's chaos. We are somewhere in between the most simple and most complex forms of existence. And this is where complexity thrives. Complexity happens at the edge of chaos. So thus complex systems have, three defining features, and all three of them are coincidentally starting with E. That is, we just discussed all three of them: evolution, emergence, and edge of chaos. So now, although we have some promising approaches to quantifying complexity like assembly theory, it must be stressed that we don't yet have a complete, definitive, and quantitative definition of complexity, which is devoid of all difficulties and problems. Thus, it is of utmost importance that we seek such a definition of complexity based on the three E's, or evolution, emergence and age of chaos. And once we get there, an entire world of possibilities will open up before us. But at this point, what is certain is that what is reasonably certain is that complexity is surely a very huge. It has a huge potential for the future of physics, and it's probably is the next big thing in physics, or we may even say the next big thing in science. So that was all for this video, guys. Thank you very much.